Today we're going to talk about graphs of rational functions. So the first thing you need to know is the parent graph of the rational function y equals 1 over x. I'm just going to go through this pretty quickly because we actually already graphed this earlier in the year. So here I have some values for x. I have -3 to +3. I also have included here 1/2 and -1/2. I think when we plot the points, you'll see why. So if you plug in -3 for x, of course, you'll get -1/3, -1/2. I'm going to skip the 0 for a minute. Because if you put 0 in the bottom of this fraction here, can you do that? Nope. So 0 is undefined. So what does that mean? Let's see here. Let's plot the rest of these points first. So we have -3, comma, -1/3. We have -2, -1/2, -1, -1, and -1/2, -2. On the other side, we have 1/2, 2. We have 1, 1, 2, 1/2, and 3, 1/3. Okay, I think you have a general sense here of probably of what's going on. Before we connect it, though, the parent rational function has two asymptotes. It has a vertical one. The vertical one is x equals 0, which is really just the y-axis. So this is what we kind of just talked about right here with this undefined. So x can't be 0 because that would make the denominator be 0. The denominator can never be 0. Okay, the horizontal one, if you watch these purple dots, they look like they're bending. I don't know that they're ever going to hit the x-axis. So the horizontal asymptote is at y equals 0. And of course, y equals 0 is the x-axis. I think we've talked about this before, but now it's in writing. y equals 1 over x, will never be 0 because you can only make a fraction equal 0 if the numerator is 0. But the numerator is 1. We can't just change that. It's not changeable. It's not variable. So the graph then will never hit the x-axis. And so then that gives us asymptotes. So asymptotes are often straight, although they don't have to be, but they often are. So asymptotes are drawn on your graph. I mean, I think you know this from the exponentials, but they are graphed as dashed lines. This is kind of tough. I was trying to make it look like the purple was dashed by putting black in it, but I don't know. I think I might have failed here. Okay. It's okay. It could be better, but I think is this the purple I had? I hate when it doesn't match. Okay. So this is the graph of 1 over x. So it bends toward the x-axis and the y-axis, but it doesn't touch either one. There we go. Okay. Rational functions whose general form is y equals a over x minus h plus k. Those are the kind we're going to focus on first. Those are set up like any kind of graph you would use transformation rules on, and they work just the same as any other function. So this is, right now, this is really stuff you already know. A, right here, A is responsible for vertical stretch and compression. If A is greater than 1, it's a stretch. If it's less than 1, it's a compression. H is responsible for horizontal shifts. Remember, x always lies, so move in the opposite direction of the sign. K is responsible for vertical shifts. Follow the direction of the sign because y doesn't lie. So when you shift, x equals h, becomes the new vertical asymptote. So whatever this number is down here, that will be the vertical asymptote, like opposite sign. And y equals k becomes the new horizontal asymptote. That's what takes everything and shifts it up. So if you take a horizontal line right here and shift it up, that's, it's going to move the asymptote. Okay, domain. The domain of a rational function of this form, because this is the form that we're talking about right now. We'll talk about other forms later. The domain is based on the location of the vertical asymptote. So the domain is going to go from negative infinity to the location of the vertical asymptote, round parentheses because it doesn't touch it, and then h to positive infinity. So h is there twice, but really it means the h is not there. That's confusing. The range is based on the location of the horizontal asymptote. So that's going to be negative infinity to k, k to positive infinity. All right, let's graph. We have y equals 1 over x minus 2. So let's identify what's going on. First, we have a horizontal shift because of the location of that 2. We always go opposite for horizontal things, so we're going right 2. So what that means is that the new vertical asymptote is x equals 2. Now, note that if x equaled 2, there would be a 0 down here, and that would not be okay. That's why there's an asymptote. Okay, so let's draw the asymptote first. And that's at vertical asymptote at 2. That looks good. Okay, kind of proud of myself. Okay, there was no vertical change at all, so the horizontal asymptote is still going to be on the x-axis. Oh, right, I didn't realize. I was thinking if I erase, it would erase the black, but it won't because it's flat. Anyway, you don't need to know that. Okay, so from here, let's put the points on. Now, once you've moved the asymptotes, you can sort of just pretend like this is now the origin. So let's look at where those original points were. So we had this point that was 1, 1, and negative 1, negative 1. So just pretend that this is the origin. 1, 1, negative 1, negative 1. And then we had over 2 up a half, over 3 up a third, and we had the over half up 2. Over a half down 2, over 1 down 1, over 2 down a half, over 3 down a third. See, once you move the asymptotes, really, the hard work is done. And you can just move the original points. Now, I realize you're not as familiar with these, with these 8 points as I am because I've been doing this forever, but you'll get better at it. Okay, let's talk about the domain. The domain has to do with the vertical asymptote. So the domain is going to be negative infinity up to, oops, oh, I have it on partial, that's why. Up to 2, and then the other side of 2 to infinity. The range hasn't changed because there were no vertical changes. So it's going to be negative infinity to 0, 0 to infinity. Okay, let's try one with a couple of different changes. So first we have this 1 down here. That's, of course, a horizontal shift. So that's going to be left 1. And that means that the new vertical asymptote is x equals negative 1. The next thing going on here is a vertical shift. That's coming from this 3, and that's going to be down 3. So the new horizontal asymptote is y equals negative 3. So that's the first thing we're going to do. We're going to draw those in. So I have a new vertical asymptote at x is negative 1, and I have a new horizontal asymptote at y equals negative 3. And I'll do my trusty little erase for the... Isn't that so much better? I used to try to draw the dashed lines and it looked terrible. And then I thought of this. Duh. Okay, but nothing else has changed besides these, besides the asymptotes. So these points are still going just like they did on the previous one. So from our pretend origin, we're going to go over a half up 1. Let me just get rid of that because that's not really there. Over 1 up 1, over 2 up a half, over 3 up a third. And then from our pretend origin, we'll go over a half down 1. Nope. Over a half down 2, sorry. Over 1 down 1, over 2 down a half, over 3 down a third. Make sure that your graph doesn't touch your asymptotes as best you can. Certainly don't let it cross it. Sometimes my arrow winds up touching it, but I don't worry too much about that. So let's talk domain and range. So the domain is going to be everything before the vertical asymptote. So negative infinity up to -1, and then -1 to infinity. Range, negative infinity up to the horizontal asymptote up to infinity. Okay, now we have some more changes here. Now this has a horizontal shift and a vertical shift. That's not too bad, but it's also got this. So that's like a vertical, well, what is that really? Hold on. So we have a horizontal shift, right 3. So that's going to be our new vertical asymptote. Will be x equals 3. We have a vertical shift, up 2. So our new horizontal asymptote is y equals 2. Then we have a vertical flip. That's what this negative in the -2 is doing. So we have a vertical flip, which is a flip over the x-axis. And then the 2 is a vertical stretch by 2. I gotta tell you, for me, that's just too much going on, and I'm gonna have to revert back to a table. So we did that with exponentials and the log, so I don't think you're gonna have a problem. So the first thing I did was I made my parent graph table. So this one here. So I literally just circled it and copied it and pasted it down here. So that's what's in these columns. Okay. Oops. Take that away. So then the order in which things have to happen. So what's happening to x? So x doesn't have that much going on. There's a horizontal shift. But if you, that's not good. I'll do this one. But everything else is vertical. So let's just do the horizontal first. So the horizontal, we're going right 3. So that means I'm going to have to add 3 to my x's. So that's what I have here. I've got me adding 3. So -3 plus 3, 0. You can do that arithmetic. Even if you have to pause the video and write it down, doesn't matter. Okay, now the y's, you have to do that in a particular order. So, I'll go back to purple here. So the y's, first you'll have to multiply them by -2. So you can do the flip and the stretch in one step sort of. And then when you get that answer, then you'll add 2 for the vertical shift. So at least you don't have to do like really 3 separate things. So first we're multiplying all of our y values by -2, except for the undefined, because you can't multiply undefined by -2. So then we get all of our answers when we multiply by -2. So just take a minute and figure that out, write it down. And then after you get all of these values here, you're adding 2 to all of them. And then you're getting these final values over here. So those are the numbers we're going to plot. Now look, if you can do this without making the table and you get the right graph, I don't care how you get it. But once the transformations just start getting really involved, I'm afraid I'm going to mess it up. So then I just go back to the table. Okay, but I am going to plot my asymptotes first, so I know that I have a vertical at x equals 3. I don't need the table for that. I know that. And I have a horizontal one at 2, y equals 2. And again, I know that. I don't have to go to the table for that. Make them dashed. Okay. Now, the dots are not going to be, it's not going to be over 1 up 1 anymore because of that 2. So rather than try to make my head think about that, I'll just use these values. Okay. So I'm just going to start at the left. So 0, comma, 2 2/3. So 0, 2, 2/3. Now remember, these are actual real points on the graph, so you're counting from the origin. We're not really transforming. We did the arithmetic behind the transforming, so now we're just strictly plotting points. We have 1, comma, 3, 2, 4, 2 1/2, 6. Okay. Then we have 3 undefined. Of course it is. That's where my vertical asymptote is. So that makes sense that that's there. And I like it there because it sort of gives me like a double check. Okay, at 3 1/2, we're down 2. Oops, that's it. Look, I counted from the wrong place. Over 3 1/2, down 2. Over 4, 0. 5, 1. 6, 1 1/3. Okay. All right. That's looking pretty good, I think. So this vertical stretch and vertical flip, so this is what they've done. So if you compare this to the graph above, do you see the arms of the graph have like switched corners? They're like in opposite like quadrants, like this is sort of in like 1 and 3. If this were centered, this is in 2 and 4. So that's what a flip will do. And then the other thing I want you to notice is that, see how this point is 1 away from where the asymptotes cross? Yeah, see, there's nothing here. That's because it was multiplied by 2. So that's why it's like over 1 up 2, over 2 up 1. That's where these points are coming from. They're coming from that 2. Okay, so that's graphing with transformations. Rational functions, though, are a very large category of functions. Oh, I forgot the domain and range. I think you know how to do that now. I'll just erase those so you can see what they are. So the graphs of rational functions get very complicated. If they are not in this form that we talked about up top, then you can't really predict what they look like. I get some form of this. I know what that's going to look like. It's going to have 2 arms. They're going to be in opposite quadrants. That's it. But rational functions, the big category, there's a lot going on, and they're not very predictable. We have ways to predict them, but it's tough. Okay. So the graphs of other rational functions is any sort of fraction that have like polynomials on the top and the bottom. Okay, so that's what that P and Q stuff means. Okay, the bottom can't be 0. That's all that's saying. Okay, so the first thing I want to talk about is what's called continuity. So the graphs of rational functions can be continuous or they could be discontinuous, and you don't know until you start investigating. So a continuous graph is like this one here, and I know it's continuous because it has no jumps or breaks or holes. So when you're looking at a graph, that's what you look for to determine if it's continuous. If you can draw a graph and your pencil never leaves the paper, it's continuous. But if you have to pick up your pencil, it's not continuous. And for this particular function, there's no value of x that makes the denominator be 0, and that's why it's continuous. What makes a rational function not continuous is whatever is going to put a 0 in the bottom of a denominator. It's the only thing that will make it not continuous. And because we have x squared plus 1 equals 0, I mean, as the denominator, if you set it equal to 0, you'd get an imaginary number. So that's an indication that there's no asymptote. You don't need one. It's just continuous. Okay, so there's no value of x that makes the denominator be 0. Okay, here's another example. This is x plus 3 times x plus 2 over x plus 2. This graph has a hole at x equals negative 2. You can see it there. So that's not a continuous graph. This is discontinuous because it has not a jump or a break, but a hole. Okay. If x equaled negative 2, the denominator would be 0. So x can't be negative 2, and that's why there's a hole there. Now, you might be saying, hey, I can cancel these, and that is true, and we'll get into that in a little bit. But this canceling of these two factors is actually what makes the hole. So we'll get back to that. Okay, here's another kind of discontinuous graph. This graph has a break because it has an asymptote. So an asymptote, the asymptote is coming from x equals 2 because that's what would make the bottom be 2. This has a scale of 2 for every block. So if x is 2, the denominator will be 0. So x can't be 2. And here the graph, they're saying the graph jumps. I disagree with that now that I see that. Now that I'm paying more attention. It doesn't jump. That's a different kind of... That comes from piecewise functions. Piecewise functions are jumps. This graph breaks. Oh, you know I hate this book. Okay. And yet I keep using it. Alrighty. So let's talk about this idea of continuity. Okay. So there are two types of discontinuity. There's removable discontinuity, and there's non-removable discontinuity. This is a lot of blah, 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 blah here, but let me tell you how it works. A hole is called removable. Anything else is not removable. So an asymptote is non-removable. You can't take it away. I don't know why they call them removable. It's kind of stupid, but whatever. I can't help that. Okay. So right here, this discontinuous graph with a removable discontinuity because this is a hole. So removable means a hole. It doesn't mean anything else. It only means a hole. Okay. This is a discontinuous graph with a non-removable discontinuity. In this case, the non-removable discontinuity is an asymptote, a vertical asymptote. And a vertical asymptote is also known as an infinite discontinuity. Because it's not just, x can't equal this number just at this dot. It's like it can't equal this number anywhere. I don't know. Anyway, it's infinite. Okay. So let's see here. Let's talk about how do we deal with this. So finding points of discontinuity. Points of discontinuity comes from the bottom being 0. Whatever makes the bottom be 0 is going to be a point of discontinuity, unless there isn't one. So the first thing you really want to do is any factoring that's possible. So when you look at this example here, you see the bottom can be factored. When you factor the bottom, you will get x minus 3 times x minus 1. So what we're going to do is we're going to set that equal to 0 to find out where the problems are. So then x would be 3, and x would be... Why do I have 0? Why do I have 0? That's bizarre. It's not 0, it's 1. Must have been tired when I made this. Okay, x equals 1. So what's happening there? Could be hard to say. These are non-removable discontinuities. I'll show you when you get a removable one. Yeah, it's down on C. But that's also vertical asymptotes, infinite discontinuities. So for these two here, these are the same thing. A non-removable discontinuity could be an asymptote, or it could be a jump, like a piecewise function. We're not dealing with jumps right now. Jumps don't really happen in rational functions. They happen in like absolute value functions, but yeah, they don't really happen in rational functions. So for right now, our non-removables will be vertical asymptotes. Okay, so what is the domain then? The domain is everything except for 3 and 1. Yeah, I must have been really tired when I did this because now I have another mistake. So negative infinity. Oh my God, I'm a mess. All right, hold on. I'm just gonna white this out and just rewrite it because it's not right anyway. Okay. So our domain, I walked right into that one, didn't I? Is going to be negative infinity to 1, union 1 to 3, union 3 to infinity. The union is just like, I don't know, that's just how they connect it in set notation. Don't freak out about it. Okay. So that's the domain. The next thing we're going to want to find are x and y intercepts. And this is all leading up to graphing these gross annoying things. So the x-intercept is when y equals 0. So to find the x-intercept, technically you would take this entire fraction and set it equal to 0. But the only way a fraction equals 0 is if the top equals 0. So you don't really have to worry about the bottom at all. Just set the top equal to 0 and you'll be good. So x equals negative 3. So negative 3, 0, that's the x-intercept. So x-intercept, set top equal to 0. The y-intercept is when x equals 0. So this is just a straight substitution. You're just putting 0 in for x. And we get 1. So the y-intercept is 0, 1. Okay. So we answered all the questions. We found the domain. We found the points of discontinuity. We found what kind they are. And we found the x and y intercepts. All right, let's try this one. So the first thing we want to do really is factor anything that can be factorable. But this denominator isn't factorable. So let's see if maybe it still equals 0 somewhere. I don't know. So we're going to look for the problems by taking the bottom and setting it equal to 0. But you're going to subtract 1, and x squared can't be negative 1. So what does that mean? If you can't make the bottom be 0, then there just aren't any discontinuities. You're good. This is continuous. So what is the domain if this is continuous? It's everything. You don't have to stop because there's nowhere you have to pick up your pencil. The x-intercepts, remember, that's you set the top equal to 0. So x minus 5 equals 0. So x is 5. So that means there's an x-intercept at 5, 0. The y-intercept, you put in 0 for x, and we get negative 5. So there's a y-intercept at 0, negative 5. And again, this is all prep for you to have to graph these. All right, let's come down to this one. This one, it's the top that can be factored. So we're going to factor that first. And the top factors to x minus 4, x plus 1. Now, if you notice here, that has the same factor on the top as it does on the bottom. And so those can cancel. When a factor on the top cancels with a factor on the bottom, that's what makes a whole. This is a whole. When a factor on the top cancels with a factor on the bottom, it's a whole. And a whole is what's called a removable discontinuity. And that's where x is 4. Where x is 4, it's a removable discontinuity, which is a whole. Now, when you cancel this, what's left is y equals x plus 1. So even though this is a crazy-looking rational function, what it looks like is the line x plus 1. But when x is 4, there's just a hole in the line. And if we go back to the top, That's what that example with the hole looked like. Look, it's just a line with a hole in it, right? Right, but look at where it came from. It was this big rational function. But when these canceled, you were just left with a line. I mean, it doesn't have to be a line, but in this case it was. Okay. Where is the hole? Well, it's at x equals 4. But how high is the hole? Well, we could find the exact location of the hole by subbing 4 into the simplified version. So this is what I would call the simplified form. This is the original form. So if you take the place of the hole, but you substitute it into the simplified form, you'll get the x and y coordinate of the hole. So that's 4, 5. So that's physically where the hole is. So there's your simplified version. There's you plugging in the hole, the x value for the hole. So we get the y value for the hole. There is a hole at 4. X cannot equal 4. It does not matter that that factor canceled. X still can't be 4. There's a hole in the graph. So the domain is everything except for 4. Negative infinity to 4, 4 to infinity. Okay, now let's come to the x-intercept. The x-intercept is when we set the top equal to 0. The problem here is that one of the factors on the top canceled. So if I just took the top and set it equal to 0, I would get sort of like a fake x-intercept. So when you're finding the x-intercept, use the simplified form. So use the form after you've done the canceling. So set that top equal to 0. And that'll be your x-intercept. A hole trumps an x-intercept. So if you have one x value and one thing tells you it's a hole and the other tells you it's an x-intercept, forget it, it's a hole. That's just the way it is. If you had an x value that in one analysis told you it was a hole and the other one told you it was a vertical asymptote, it's a vertical asymptote. An asymptote trumps a hole trumps a point. Okay. The y-intercept shouldn't matter which version you put it in at all. I just put it into the top. It doesn't matter because that factor cancels, so whatever you put there is going to cancel. So there's my y-intercept. Okay. Okay, let's see here. All right, so these are just like the ones from above. Oh, looks like I forgot to block something out. So I want you to try these. I know it's a lot of work, but try these and then, so pause the video and then come back because you got to practice on your own. Okay, I hope at least 15 minutes have gone by. Okay, so the first thing you want to do for A is factor. All right, the bottom, what would make the bottom be 0 is 4 and negative 4. Do they cancel with anything on the top? No. Then these are non-removable discontinuities. These are infinite discontinuities. These are vertical asymptotes. The domain is everything that's not 4 and negative 4. Oops. Okay, x-intercept. That's when you take the top and set it equal to 0. But the top is 1. You can't make 1 be 0, so what does that mean? That means there's no x-intercept. Not your problem. Maybe it just doesn't touch the x-axis. That's okay. The y-intercept is when x is 0. So that is 0, negative 1/16. I would just, there's a lot of questions. So anytime there's a lot of questions, I would just make sure that you've answered them all. So domain, points of discontinuity, removable or non-removable, x and y intercepts. It's a lot to do. Okay, let's look at B. B can be factored on the top, can't be factored on the bottom. Nothing is canceling. Set the bottom equal to 0 to find out what will make the bottom be 0. But there isn't anything because you can't make x squared equal negative 3. So what does that mean? There are no discontinuities. This is a continuous function. If you don't have a discontinuity, the domain is everything. The domain only skips numbers if they're discontinuities. The x-intercepts come from setting the top equal to 0. You don't need to worry about the bottom. So x minus 1 times x plus 1 equals 0. Might as well use your factored form because it's easier. So x is 1 and negative 1, and that means you have two x-intercepts, and that's okay. You can cross the x-axis 100 times. It doesn't matter. The y-intercept is when x is 0. Simplify. 0, negative 1/3. All right, for C, we can factor the bottom on C, but look at what happens. I have an x plus 1 factor on the top and the bottom. Those cancel. And so what does that mean? A couple of things. It simplifies to 1 over x plus 2. So in this case, it would not be a line with a hole. It would be a rational function looking thing with a hole. But x still can't be negative 1 because it still would make the bottom be 0. And that's what's a removable discontinuity. When the factor cancels, that's what makes a hole. Where is the hole? Take this negative 1 and plug it into your simplified form, and you'll get 1, because 1 over negative 1 plus 2. Oh, there it is right there, sorry. Okay, however, there is still a factor on the bottom. X plus 2 is still there, and that is not removable. That's a vertical asymptote. So in this particular question, you have a hole and a vertical asymptote. That's okay. You have a hole in one location and a vertical asymptote somewhere else. That happens. Do you see why they're not very predictable? You have to do a lot of work to be able to predict what they're going to look like. To find the x-intercept, you're going to use the simplified form. So we're going to use this to find the x-intercept. Otherwise, we're going to think there's an x-intercept at negative 1, and there's not. So we're going to use the simplified form, which is setting the top equal to 0, but the top is 1, and you can't make the top be 1. No, you can't make the top be 0 because it's 1, so there are no x-intercepts. That's fine. That's not your problem. Substitute 0 in for x for the y-intercept. You can see I used the simplified form. It's not going to matter. And that's 1/2. So 0, 1/2. Okay. We're just one more thing, and then we'll break. Vertical asymptotes. Vertical asymptotes come from what makes the bottom be 0 unless the factor on the bottom has canceled with 1 on the top, because that's what makes a hole. Okay, so let's look here. What are the vertical asymptotes? So what you have to do is look to see if anything is going to cancel. Is anything going to cancel here? No. So because nothing is going to cancel, you're getting 2 vertical asymptotes. That's also okay. You can have a million vertical asymptotes. It doesn't matter. So x equals 2 and x equals 3 are both vertical asymptotes. And just remember their other names. They're non-removable discontinuities, and they're also called infinite discontinuities. And they're excluded from the domain. You have to take them out. Okay, let's look at the second one. Anybody canceling there? Nope. So I'm going to have 2 vertical asymptotes at x is 1 and x is negative 3. Okay, now here, look here. Oh, I already shouldn't have blocked that out. The x minus 2's are going to cancel. So that's not going to make a vertical asymptote. That will make a hole. But they're not really asking you about holes on this. So they're only asking you about vertical asymptotes. So the vertical asymptote is coming from the guy who's left. So x equals negative 3 is a vertical asymptote. What's happening at x is 2? It's a hole. The question really was just vertical asymptotes, but I don't want you to lose sight of the fact that what was there was a hole. Okay, so on this one, what are you going to have to do first? That's right, you're going to have to factor first. And when you factor, one of the factors on the top cancels with the bottom. So what does this bottom factor make? So x is negative 1. That's a problem but it's not an asymptote because that factor canceled. That's what makes a whole. The factor that cancels makes the whole. Is there anything left on the bottom now? What's down here now? It's just x minus 1. There's nothing on the bottom, right? There's just a 1 on the bottom. If there's nothing left on the bottom, then there are no vertical asymptotes. It's not continuous because there's still this whole, but it's not continuous and there's no vertical asymptote. If this simplifies to x minus 1, then this is a line that looks like this, right? It's just a line. But at negative 1, there's a hole. And we show a hole by literally putting a hole there. I mean, really, there's just nothing there, but it's emphasized nothingness. Okay, so you can stop the video for today. I do have some more to do, but we'll wait on that for the next time. So you're good to get started on these assignments.